Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Andrey Tyarin. Andrey received his bachelor and master degrees in applied mathematics and physics from Moscow Institute of Physics and Technology. Currently, he is a PhD student and he has been working at the Institute of Information Transmission Problems of the Russian Academy of Sciences. He is one of the authors of Reconfigurable Intelligent Surface created at the IITP, and today he will share with us some insights on how to produce such devices. Andrei, the floor is yours.
Good afternoon, everyone. Today I'm going to tell you about the principle of design and operation of reconfigurable intelligent surfaces. So I have titled my presentation Architecture of Reconfigurable Intelligent Surfaces from Design to Implementation. If you have any questions, I'll be happy to answer them at the end of my talk. Here's our plan for today. Firstly, I will tell you about the Reconfigurable Intelligent Surface, or shortly RAS, and its structure. Then we are going to discuss the main RAS functions. After that, I will briefly explain the principles and principle of RAS beam steering. Next, I will elaborate on RIS cell structure and its main components. After that, I'm going to cover RIS control system. And at the end of my talk, I would like to discuss the current open issues connected with RS hardware part. Now let's start. What is RS? RS is a flat structure consisting of unit cells. These cells can create the required phase shift in reflected electromagnetic wave compared to incident wave. Here you can see a schematic image of RS and its unit cell, or UC for short, is highlighting on the right. Why do we need RS? RS is prospective technology. It holds tremendous potential to enhance the capacity and coverage area of wireless networks. With RS, the channel condition can be dynamically reconfigured in order to adapt the changing environment or to optimize network performance in real time. RS can be used in indoor environments where the signal strength and quality are often degraded by obstacles and interference. For instance, it can be deployed at offices, homes, and public spaces like shopping malls and airports. Moreover, by placing RIS on building facades or other outdoor structures, wireless signals can be steered and focused towards specific areas, providing constant coverage and higher data rates. Now, let's talk about RS structure. These slides demonstrate a common structure of RS. RS consists of low consumption scattering elements named UCs, as I mentioned earlier. Each UC is made of metal and dielectric and contains a reflecting element and a tunable chip. A reflecting element is typically a rectangular metallic patch. The tunable chip is normally a semiconductor device that causes the change in parameters of the reflected EM wave, which are phase and amplitude. These shifts are controlled by bias voltages applied to tunable chip of each UC by the RS controller. Later, I will talk extensively about UC and RS control. But now, for a better understanding of the UC structure and operation, I should first tell you about the RS function that I will implementing today. The most common function are beam steering, beam forming or focusing, polarization change, absorption, phase shift keying, and beam splitting. Now let's discuss every function one by one in detail. For a better understanding, firstly, I want to tell you about beam steering and beam focusing. Beam steering refers to reflection described using principle out of conventional Snell's law. In that case, the reflection angle can have any value. Beam steering is realized by creating equal phase shift difference between adjacent elements. This RAS function helps us in reflection of a signal from the transmitter to receiver, thus increasing its signal strength. Via beamforming, ROS reflects the power of the EM wave and focus it in a certain point in space. To implement beamforming, it is necessary to create different phase shift differences between adjacent UCs, unlike beam steering. With the help of beamforming, one can amplify the signal from the receiver on the transmitter even more than beam steering. Now I want to discuss polarization change. This function changes the polarization of reflected EM wave and works with beam steering and beamforming together. To change the polarization of the reflected EM wave, AEC need to have anisotropic properties. For example, it is possible to change polarization for 45-degree polarized EM wave via RIS operating only with horizontal polarization. This was realized due to anisotropic properties of UC, which made a phase shift in the horizontal component of the wave, but none in the vertical one. However, to switch from linear polarization to circular and otherwise, unit cell itself has to be divided into separate elements, and these elements' impedances are needed to tune independently. Let's talk about absorption now. Some RSs are able to absorb an incident EM wave with an absorption coefficient of more than 90% in a given frequency range. RS with pin diodes can absorb EM wave in a very narrow frequency band with a width of most 5 megahertz, regardless of the carrier frequency. RS with varactors is applicable for absorption in a wider frequency band. Absorption makes it possible to use RS as a sensor. For example, the angle of incidence and polarization of the electromagnetic wave can be determined using absorption. Also, absorption can be used for energy harvesting, providing RS with additional power. Now let's discuss phase shift keying and beam splitting. Phase shift keying, or PSK, is a type of phase modulation that changes the phase of the carrier signal to organize transmit data. This function is performed by creating a phase shift at the UC with a value corresponding to a digital sequence. PSK is mostly realized in RAS with varactors due to their wide phase shift range. Beam splitting creates several reflected beams from a single incident. One of the way of realization of this function is grouping several adjacent UCs into one of the into one and forming a chessboard distribution of states on new UCs. Thus, by changing the size of the new UCs, it is possible to change the number of the beams. And beam splitting can be used for multi-user transmission when each of the beams reflected from RAS on a separate user device. Now I want to briefly tell you about beam steering principle. Consider an monochromatic incident plane wave as shown on slide. Reflection is a key process of interaction between RAS and the incident EM wave. RAS top layer serves as a reflecting surface. For simplicity, I explain IRS operation principle for one-dimensional RAS. The same approach can be applied to two-dimensional RAS. Let delta x and delta phi be the distance and the phase shift difference between adjacent UCs, respectively. The phase shift of single UC is the difference between the incident wave and reflecting wave phases. Additional phase leaps between adjacent UCs leads to phase discontinuity throughout the top RIS layer. In that case, the incident angle does not equal the reflection angle. In other words, the anomalous reflection occurs. This phenomenon is described by generalized Snell's law, which you can see on the slide. It's a first equation. With this equation, it is possible to calculate phase shift difference between adjacent elements in that wave to reflect the incident angle theta E at the angle theta R. This is expressed as a second equation on slide. And as I said earlier, it can be extended to the dimensional case and for focusing. UC is a key component that defines most of RIS functionality. And now I want to describe the UC structure, and I describe UC structure which consists of at least 3 layers. The bottom layer, it is a metallic layer, and its needs for grounding. The top layer necessarily contains reflecting element, and its dimensions define the RIS operation of frequency band. The tunable chip is also located on the can be located on the top layer, but it can be placed on the lower layer. The tunable chip is required for changing the UC impedance. The layer between top and bottom is made of dielectric. Its important characteristic is dielectric loss tangent, dielectric permittivity, and its thickness. Permittivity defines the reflected EM wave amplification. The smaller permittivity, the stronger the amplification. Loss tangent is a tangent of a phase shift difference between current or voltage in real radio components and ideal ones. Therefore, a decrease in the loss tangent directly corresponds to decrease in UC losses. The choice of dielectric thickness is not a straightforward task. On the one hand, with an increase in the thickness of the dielectric, energy losses in the dielectric decrease. On the other hand, it reduces the maximum range of the phase shift. The insulating layer is commonly made of FR4 and F4B fiberglass. The distance between adjacent UC equals to half wavelength. If it exceeds half wavelength, grating lobes of EM wave propagation arise. Also, since beam steering is one of the frequent risk function, the maximum deflection angle, theta max, is an important parameter, and the maximum distance d max between adjacent UCs is expressed on the slide. Therefore, the distance between the elements equal to half the wavelength is the optimal value. Now I'll explain how RIS configuration provides the necessary phase shift difference. UC size is smaller than the wavelength of the EM wave RIS interact with. Thus, UC is modeled as a transmission line. Using this approach, it is possible to find impedance value via reflection coefficient to address a certain difference of phase shift between adjacent UC at the EM wave with circular frequency omega. The complex reflective coefficient gamma of the UC is defined by its input impedance and free space impedance that sub-zero approximately equals 377 ohm the following way. And input impedance consists of impedances of reflecting element and tunable chip. Also, when the input impedance value is set almost equals to free space impedance, reflection coefficient approaches zero, what helps to realize absorption. A reflecting element is necessary, as I mentioned earlier, for interaction with incident EM wave. A typical reflection element is a patch. Usually, form of the patch is rectangular. However, some prototypes use peculiar shapes such as bow tie structure, fractal structure, fishnet-like resonators, and so on. However, such shapes have rather narrow amplification. For example, the fishnet-like resonator is applicable for absorption. The fracture structure acts as a rectangular patch, but it has small dimensions. Sometimes you see has several patches connected to one tunable chip, but the rectangle patch is more universal in the sense of function that RIS can implement. Moreover, a rectangle patch is a good trade-off between bandwidth, phase shift range, and losses. And now I want to tell you how to calculate the patch dimensions. These dimensions denote as WP and LP play a crucial role in determining the operational frequency of RRS. In order to achieve a resonant frequency FR for the RRS, these dimensions can be calculated using expressions on the slide. A tunable chip is a device that changes the UC impedance, as I mentioned earlier. Nowadays, prototypes include various tunable chips such as RF switches, relays, optically programmable capacitors, complementary metal oxide semiconductor integrated circuits. But however, pin diodes and varactors are the most common tunable chips, and we cover them at length. We start with pin diode. Pin diode is a diode with white undoped semiconductor I-type region between heavily doped P-type and N-type regions. It has two operational states, forward bias or on, and reverse bias or off. In the on state, the pin diode acts as a variable resistor with a resistance inversely proportional to the bias current. In the off state, pin diode acts as a capacitor. And here you can see the equivalent scheme and impedance of for each pin diode state. One of the key advantages of pin diode is their low control voltages, which are typically under 5 volts. When the diode is in the on state, a current through it is around 10 milliamps, while in the off state, the current consumed is negligible. Pin diode has a switching time of less than 100 nanoseconds. The pin diode location determines the polarization of the EM wave on which the phase shifting occurs. Picture on the right shows the dependence of the phase shift on the frequency of UC for both pin diode states for normal incidence of linearly polarized EM wave. The parameters of the UC were selected so that a phase difference of 180 degree was achieved at the frequency of 5.3 gigahertz. Since a pin diode has only two states, the value of phase shift difference between them should be 180 degree for a single bit phase quantization. Now let's discuss its advantages and disadvantages. Its advantages: pin diode is mainly used to create a phase shift of 180 in two different states, thus being applicable as binary element for a simple control. Pin diode has a low level of bias voltage and fast switching speed. And what about disadvantages? Pin diode serve as a discrete element, limits the RIS functionality. For example, it decreases the precision of beam forming. Moreover, the pin diode causes a mirror beam effect when a parasitic beam symmetric to the main beam appears. Pin diodes are effective only in a narrow band because broadening the bandwidth leads to the deviation from 180 degree. And pin diode has a large current consumption in the on state. Most of the disadvantages of pin diodes are overcome by structural solution. For example, one-bit state discretization is overridden by using multiple pin diodes in one UC. A narrow band can be fixed by using more complex UC structure with thick dielectric. However, such solution complicate the structure and for multiple pin diodes case, potentially increase power consumption. RS with pin diodes typically performs beamforming, polarization change, beam splitting, and beam steering. Now let's talk about varactor. Varactor is a diode with variable capacitance, which is determined by applied bias voltages. Usually applying a control voltage ranging from 0 to 30 volts is necessary to achieve the complete range of capacitance values for varactors. Varactor draws about 50-100 nanoamperes of current. The equivalent circuit and the impedance of varactor you can see here on the slide. As for pin diode, the varactor location determines the polarization of the M wave on which the phase shifting occurs. The picture on the right illustrates the relationship between the phase shift and the frequency of the UC with the varactor for multiple capacitance values under the normal incidence of linearly polarized EM wave. The parameters of the UC were selected so that 5.3 GHz is the central frequency of the band, where difference of phase shifts between the curves remains almost constant. Thus, by changing the voltage on the varactor, we adjust the phase shift in range from 0 to 300 degree. Now let's discuss varactor's advantages and disadvantages. And its advantages: varactor performs continuous impedance tuning, thus providing fine frequency, amplitude, or phase tuning of reflected EM wave. RIS with varactor operates in large bandwidths, approximately 1 GHz for absorption and 200 MHz for beam steering. Varactor has lower current consumption and its disadvantages. Varactor has complicated control and requires additional elements such as lever shifters implementation in each UC. Varactor is usually controlled via high analog voltage up to 30 volts. Varactor lack most of pin diodes disadvantages, such as limited number of phase shift states and low efficiency in large bandwidths. Moreover, most of the varactor's disadvantages can be overcome. The usage of high analog voltage can be avoided by using lower control voltages, thus performing the necessary functions, albeit with minor efficiency loss. Varactor control is facilitated by using a fixed number of control voltages. Nevertheless, only varactor are suitable for absorption in a wide range, about 1 gigahertz. Still, relying on the existing research, I provide the following recommendation: which tunable chip we need to choose, varactor or pin diode. You need to use a varactor or pin diode for beam steering, beam forming, polarization change, and beam splitting. But for absorption in PSK, you need to use a varactor. Use a varactor when the bandwidth is more than 40 megahertz. Otherwise, use a pin diode. Use a pin diode for 1 bit UC for implementation of beam steering and beam forming. Otherwise, use a varactor. Note that this recommendation given for simple EC structure, like this on the slide, with a single pin diode or varactor. Now I'm going to tell you about RAS control system, and I start with the RAS controller. Current RAS prototypes demonstrate that microcontrollers and field programmable gate array or FPGA are used as RAS controllers. For instance, Arduino Mega is one of the most common RAS controllers based on a microcontroller. It has around 50 digital input-output pins, 15 of them capable of using 8-beam pulse width modulation or PWM. The controller's maximum clock frequency is 16 megahertz, and it supports I2C, SPI, and UART interfaces. The parameter of FPGA depends on the used model, but usually its maximum clock frequency and the number of digital outputs are more than of Arduino. Now I want to talk about features that define the controller choice. RAS parameters that defines the selection of controller and controller system are the type of tunable chip and the number of UCs. Let's me describe how to choose the controller according to these parameters. Pin diodes and varactors are the most common types of tunable chips. Pin diodes requires 2 voltage levels for its state adjusting. One is greater than 0, and the other is less than or equal to 0. Since digital output meets these requirements, that there are no control limitation for UCs with a pin diode. In contrast to pin diode, UCs with varactors require analog or digital outputs together with amplifiers, level shifters, digital to analog converters, or pulse width modulation with filters. The amplifier allows you to use the entire range of capacitance for varactor. The lever shifter is used to control a high analog signal with a digital signal. Therefore, the required analog voltage on the varactor can be set via digital signal. This is especially useful for varactor-based RIS with functions such as beamforming and beam steering. If controller lacks analog outputs, digital to analog converters realize conversion from digital signal into an analog one at the output pins. Other way to get an analog voltage using a digital outputs is to use PWM signal with a low pass filter. PWM signal is converted into analog one, for example, via an RC low pass filter. The number of UCs in IRS is also an important parameter. However, even FPGAs have a limited number of output pins. Current RISC prototypes use three-way ways of overcoming this limitation, applying the control signals consequently, grouping the control UCs to control them with one signal with minimal RISC performance losses, and using control hierarchy. And now I want to share with you my RISC prototype. Picture on the slides show the design with my colleagues from Wireless Network RISC prototype with 12 times 16 unit cells. The RAS has a three-layer structure. The top layer consists of pin diode and a square metallic patch, 25.5 millimeter long. The middle layer is an FR4 insulator with permittivity approximately 4.5, loss tangent approximately 0.02, and thickness equals 1.6 millimeter. The bottom layer metal for the grounding. We find the appropriate sides of the patch using the CST Microwave Studio to obtain a pi phase shift difference between on and off states at 2.605 gigahertz, which corresponds to the central frequency of band 38 of LTE. Our prototype has a model design and consists of 4 sub-RISs. Each sub-RIS, sub-RS, contains 48 UCs with independent phase tuning managed by Arduino Mega. As a RS controller, we use a single board as a central RS controller. We use a single board computer, Raspberry Pi 4, which is connected to 4 Arduinos. It supports Wi-Fi connection to receive control commands and feedback information from user device, such as laptops and smartphones. Even such simple RS prototype doubles downlink and uplink throughput for edge user in outdoor and outdoor to indoor scenarios in LTE. Finally, let's talk about the current open issues. First is the maximum set of RS functions. There are various sets of requirements that is necessary to achieve in modern wireless technologies. One of the popular tasks is to increase the capacity of wireless network. However, this task can be solved in various ways using IRS. For example, IRS can be used for beamforming of transmitting signals, signal on the receiver, or interference cancellation from the other device. For these purposes, IRS requires different functionality. Beamforming for signal amplification or absorption for interference cancellation. Thus, the problem arises which RIS functionality is necessary to deploy for specific tasks such as capacity or coverage improvement, transmission delay reduction, and so on. The second issue is parasitic effects in IRS. Most papers related to IRS prototyping pay no attention to various parasitic effects. And individually, each of parasitic effects already has a significant influence on the impedance of UC. Parasitic effects can be caused by solder, for example, on contacts of the tunable chip, mismatch between the original specified sizes and the manufactured ones. The impedance is also affected by the incident angle of the incoming EM wave. With an increase in the incident angle, the phase shift range of the tunable chip decreases. Therefore, studies devoted to research on the influence of all effects are all of these effects are relevant. The last one, methods of power increase and method risk consumption degrees. At the moment, risk is assumed to be a passive device. There are prototypes with a consumption of about 100 watt and about 1 watt per 1,000 elements. Obviously, RS cannot be completely passive, but it's necessary to decrease its energy consumption. In the outdoor scenarios, if RIS has solar cells, for example, that will be provide it enough power. In indoor scenarios, it is assumed that one battery supplies enough power for a long time. However, also energy harvesting can be an additional energy source in both scenarios. However, there are very few works devoted to reducing RS power consumption. Therefore, this issue is a vast area of new research. And that brings me to the end of my talk. Thank you for your attention. And now I'm ready to answer your questions.
Thank you, Andrey, for your interesting presentation. Do we have any questions from the audience? Okay, maybe the first question from my side. Could you tell us the approximate price of the developed prototype?
Approximate price of developed prototype is sorry, I need to calculate.
It's just an approximation. For example, $10, $100, $1,000,
No,
$10,000.
200 or $300.
Okay, thank you. So the next question from Alexey.
Okay, thank you for your talk. As you said, your RAS prototype provides about 2 times gain in throughput. As I understand, it is experimental result. Can you somehow describe this experiment?
I'm trying because without pictures it will be difficult. First experiment it is a indoor to outdoor scenario. A distance between RS and TX is around 200 meters. Between RS and RX around 3 or 5 meters, and direct link between TX and RX is around also 200 meters, and we have direct link between RX and TX, but it was weak. So we need to constructively sum up signals from RS and direct signals in first case, and the second scenario was outdoor scenario, and the distance between RS, RX, and TX was around 1.7 kilometers, and the distance between RS and RX was around 3-5 meters. And again, it will be direct link, but it was weak.
Okay, the next two questions from Artem.
Yeah, thank you very much for interesting talk. So actually, the first question was asked by Alexei about the performance, and the second question was about energy consumption. So, for example, if we put the RAS for 1 day, how much power it will consume in active state? So, do we need, for example, the constant source of energy, or we can use batteries for RAS?
It is an interesting question, and I haven't seen such research, but for my opinion, we need to reduce RAS consumption as we can, as such a way that in outdoor RIS can be supplied by only solar panels, for example, which will be integrated in RS itself, and indoor it may be battery supply. So I think.
But about your particular device, did you ask yourself how much power per second, per hour is consumed by the device?
Actually, no.
So it could be interesting to have exact numbers or some approximations. Thank you.
Thank you for your question. Yes.
Okay, one more question from my side. Do you plan to make some new prototype of RAS taking into account all the experience which you achieved since the development of the first prototype, and what will be the changes in the second version of prototype?
I want to make a new prototype. Yes, and I think main difference between old one and the new one will be that in new prototype it can operate in two polarization, and current prototype can work only in one linear polarization. Also, I want to make at least 2-bit phase quantization, not one, and maybe higher frequencies like millimeter wave. And for that case, pin diode maybe is not a good choice, and in the new one I see as a tunable chip varactor, as varactor.
Okay, thank you. So I guess that's all for today. Let me thank Andrey for his interesting presentation, and I also want to thank all the audience and the people who asked the questions. So thank you. Goodbye.
Goodbye, everyone.